Okay, to get more practice with how we balance redox reactions by the half reaction method, I want to do a couple more examples on this recording to give you more ways to figure it out. Some examples are more complicated than the other. Remembering that these are the steps we will follow. I'm not going to write them all on the screen this time, but I'm going to work out the examples in detail to help you see how we go from writing the unbalanced equation, figuring out where the oxidation and reduction half reactions are, balancing the half reactions with everything but oxygen and hydrogen, balancing the half reactions for oxygen by adding water, balancing the hydrogen by adding H+, and after we do that, then we add electrons to balance the charge for each half reaction, and then make each half reaction multiplied by a factor to get the electron count the same in both. Then we add the two half reactions together, canceling out the electrons and everything else to come up with a final result. Okay, here's an example that comes straight out of the textbook in the list of suggested problems. They're always good to work on as many of those as you can, but let's do one together. All right, so we're going to have a balanced net ionic equation for the reaction in acidic solution giving this initial unbalanced net ionic equation. Okay, so step one is to identify the oxidation and reduction half reactions. And we have to stare at what's going on here to make sure we're not getting mixed up. So zinc is going, look at oxidation numbers or oxidation states to help us to figure out what's going on. So zinc is going from an element to an ion. So 0 to +2, that's not so bad. The vanadium has an ion that I don't know the name of in the left side. So, okay, I don't want to name it. But on the right, it's got a +3 ion, so that's its oxidation state. So what's the oxidation state of the vanadium on the left side of the reaction? Well, in this case, the vanadium has to have enough negative charge that the overall, enough charge to go with the -2 of the oxygen to get up with +2 overall. So apparently, if there's one of each, the vanadium must be +4. So the vanadium is getting reduced, so the reduction is going to be a reaction of the vanadium oxide, whatever that's called, aqueous. You don't have to know the name, it's fine. Turning into the vanadium +3, vanadium 3 ion. The oxidation step then is the other part. The oxidation half reaction is the zinc being, excuse me, I bumped something, oxidized to its ion, the zinc 2 ion. And that's the first thing we got to do. Okay, now step 2 is then to having identified those two half reactions is to balance the atoms of each of these things. Hey, this one's slick. It doesn't require nearly as much balancing because there's one vanadium in each and one zinc in each. Okay, so far so good. Then we have to add something to account for the oxygen in the vanadium reaction. Well, if there's oxygen on the left side, there better be oxygen on the right side. So add water. These are always aqueous reactions, notice. So there's nothing wrong about including water in the process. It turns out that it's necessary, and it's always a liquid. But how much water do we need? Well, we just need 1 oxygen. So that works to have 1 there, but having done that means we need to add some hydrogen to the other side to make the hydrogens balance out, so there better be 2 hydrogen ions. Again, these are going to be aqueous. All right, so now the hydrogen and the oxygen are fine on that reaction. There are no hydrogen or oxygen to add on the oxidation reaction, so that's simpler. Next, we have to balance the charge. Balancing the charge for each half reaction. Let's do the second one first. It's the easiest. It's the overall charge here is 0, so charge on the half, that reactant side is 0. The charge here is, oh yeah, +2. So we have to add some electrons to make that half reaction come out right. Well, remember, oxidation is losing electrons, and so electrons should be on the product side of the oxidation half reaction. The reduction is the opposite, and it should be gaining electrons. So we're expecting to put electrons on the left side of the first reaction. So let me see if I can move this. Maybe not. Okay, so I'll put some electrons on the left side, but how many do you need? Well, what's the overall charge on each half? Well, this half, the overall charge is +3 because there's 1 vanadium ion. And on the left side, we have plus 4. If you see 2 hydrogen ions, and the vanadium oxide thing, whatever it is plus 4. And so we have to add an electron. So an electron now will make those come out even to have a balanced charge left and right. That wasn't very many parts to add, but it gets the job done. Okay. So the next step from there is to make sure use a multiplier so that we have the same number of electrons on both sides. Oh, okay. So the first reaction only has 1 electron, and the second one has 2. So we'll multiply everything in there times 2, and then we sum the whole business up and see what we get. Okay, this takes very careful work because it's easy to lose parts if you're not looking. I'm going to start with the zinc reaction because it's easier to write. Zinc has no changes, and in its half reaction, we'll leave it alone. So we take the reactions of each process and put them together. So we have now 2 electrons because we have to multiply everything there times 2, and 2 of the vanadium VO plus 2 ion, whatever that is. We don't have to know its name. And then twice as much of the hydrogen now will be 4 hydrogen ions, and they're aqueous. That's all the reactant species. Good. Now the product species from the 2 half reactions are, we'll go back to the zinc part, so the zinc 2 ion, we didn't have to change that, and 2 electrons. So far so good. And then we'll do the vanadium reaction. Remember, everything there has to be multiplied by 2 for this all to come out even. And it's still vanadium plus 3 aqueous, and 2 in front of the water, liquid. All right, having done that, we're getting close now because we can begin to see what things are duplicated left and right a little bit. Clearly, the electrons, because we made them come out even. So there's 2 electrons here that don't need to be shown in the overall process, but nothing else. There's water left and right. Nope, there's only water on the right and hydrogen on the left, so we can't cancel those out. And so now we simplify. Simplify the process. Simplify the description of the reaction. So the net overall balanced net ionic equation here that shows everything in a complete fashion. Zinc solid reacts with 2 of this VO plus 2 cation that's aqueous, and 4 hydrogen ions are necessary for this reaction to come out balanced because the product is zinc 2 cation aqueous and 2 vanadium 3 ions aqueous and water twice, 2 H2O. Aha. So that is a relatively less complex example, but it's totally worthy because it gives you all the steps. For the benefit of repetition, let's do one more example. Here's another one from the textbook. Oh, I got an extra dot in there. Never mind the dot. And so silver reacting with nitrate, this is something funky, where the silver is going to become silver ions. The nitrate becomes NO2 gas. We've got to do the same kinds of things. We're going to look for the oxidation and the reduction half reactions. So where do we go? The silver is turning into silver ions, and those are aqueous. And the nitrate is aqueous ions turning into NO2 gas, which is oxidation, which is reduction. Remember, losing electrons is oxidation. So that is, in fact, what's happening to the silver. It is the oxidation half reaction. This silver is losing electrons to become an ion. And that other reaction, the other half of the process, is the reduction half reaction. The nitrogen in the nitrate ion is losing an oxygen and ends up as NO2 nitrogen dioxide, which is a gas. That may not look correct. Okay, so we've identified that. Next step is to balance the atoms in the 2 processes, which are not for anything besides oxygen and hydrogen, which is easy because there isn't anything else. So instead now we have to fiddle around with adding water to take care of the oxygen differences. Apparently we need some more oxygen on the right of the reduction process, so put in water. Water is always available in aqueous processes. And in order to do that, there better be some hydrogen ions on the other side to account for where they end up in the process. And so far so good. The atoms are all balanced, but now we have to figure out the charge. All right, so the first reaction, no charge on the left, +1 on the right. Oh, easy. We had to take away an electron from the silver, just one, to become silver ions. What about the second one? We should be a reduction process, so it should be some kind of electrons over here, but how many will it take? Well, let's think about it. On this side over here, the total charge is 0. Nothing with charges. And so on the left side, we have 2 and -1. And so this better be another electron needed to add up to the 0. And so it'll just be 1 electron. -1 with another -1 +2 plus a +2 gives you 0. OK, so 1 electron is all we need. Ah, simple. This is a much cleaner example than some that we've seen. When we've gotten to that point, the atoms are balanced, the charges are balanced. We combine the two processes and figure out what the overall process looks like. So an electron adds to a nitrate ion, aqueous, and 2 hydrogen ions, aqueous, and a silver solid atom to make silver ions. I'm not writing in these particular order, as you can tell. It's not really important. Plus another electron, which in a moment will be dropped out. And the nitrogen dioxide gas is formed, as is water, a product. And so when we simplify the whole process, we take out the things that occur left and right. So that means we take out the electron here and the electron here. And the resulting process looks like this. Well, let's do it in the order that's shown at the top. So let's start with silver. And we're going to add nitrate ions to it. But it's not just that. Now we have to have acid present because it says so. We're going to do this in an acid solution. This is common for these kinds of examples. Some are done in base, but we aren't going to do those examples for this semester. We don't need to. We keep it simpler without getting us confused with that detail today. And so there are the 3 reactants. The 3 products then are silver, aqueous, and nitrogen gas, sorry, NO2 gas, nitrogen dioxide, and water. That is the balanced and net ionic equation for this redox process. Wow, exciting and complex, but sometimes some examples are better than others and not as detailed to write through. I hope you find these helpful. Please ask more questions as needed, and good luck on your homework. See you in class.